Hello, everyone. Let me know if this sounds familiar. You've created a model, a powerful model, but you actually don't know the intricacies of how it works. It's a black box. You don't know how a change in the inputs will affect the outputs, and this can make it incredibly difficult to get buy-in from your stakeholders. A clear example, which I think everyone in this room today will have, are LLMs. To be clear, we're not going to talk about LLMs today, just if everyone else is mentioning them, we think we should too. So, somewhere, a wizard has put together this LLM. You drive it by giving it a prompt, but you have no idea how adjusting the input slightly, like removing a comma or changing one of the words, will affect the outputs that you get from it. So today, we're going to talk to you about how we gain real-time insights from our models to make more informed decisions so that you can too. But before we do that, we work in sports betting. So let's keep this betting related. We've practiced this talk maybe just 10 times. And we think it takes about 34 minutes to run through the presentation. So that's our line. But this is game day. Are the nerves going to get to us and are we going to talk way quicker through this than normal? Or am I going to forget every line that I've prepared and just stand up here like a melon? So, quick little raise of hands. Who thinks we're going to go over 34 minutes? Okay. No, we'll just rattle through it at the end. Changes his bet. And then who thinks we're going to go under? Okay, so the room's betting me over. I don't know if that's you giving me a vote of confidence or not, but Ethan, start a timer and take us away.
Hey, everyone. So, as it says behind me, we work at DraftKings, which is a company that works in the sports entertainment space. We were founded in 2012 in Boston, and we initially focused on daily fantasy sports. But when the US legalized sports gambling in 2018, we entered the sports betting space, and we're now one of the preeminent sportsbooks in the United States. Now, some of the people in this room who are more astute and already awake at 10 a.m. on a Tuesday will be asking yourselves, why is a Boston-based company being represented by two people with British accents? And the truth is, when DraftKings pivoted into sports gambling in 2018, they acquired a UK-based company, which is how both Aaron and I ended up here. As it says behind me, we both work in a team called Sports Intelligence. And our primary job function is calculating the odds that go on site. And there are two really important things to take from this slide. The first one is that when we talk about odds, what we're actually talking about are probabilities. As an event becomes less likely to occur, the eventual payout to the customer has to be higher to justify them betting on a less likely event. The second one is that even though both Aaron and I have very similar job titles, we do very different things at DraftKings. I work on our baseball pricing engine, and I'm here mostly to tell you about how that works. Whereas Aaron works on our ML platform team, which is primarily responsible for making sure our models integrate smoothly with other components, they run as quickly as possible, and most importantly for this presentation, that we have really clear and actionable insights coming from our models.
So now we've covered what DraftKings is and who the two of us are. In this presentation, we're loosely going to discuss how sports betting has changed, how we've had to adapt to model it, why that's not been enough, and then another layer of a solution that we've put on top, powered by streaming to help us get there. So, how has sports betting changed over the years? Well, DraftKings' goal is to become the home of live betting, and we are succeeding. A recent Eilers and Krejcik report ranked us as the #1 US sports betting app. And this is a feat attributable to a wide array of teams at DraftKings, far past myself and Ethan. But one of the key driving factors for this that me and Ethan do contribute to is the sports betting content. These new bet types are just far more entertaining than their old counterparts, and they're far more personalizable to you and your tastes. One of the examples we can talk about today are microbets. And an example of this can be seen for baseball on the right-hand side of the screen. But in the context of our example of taking a bet on the length of the presentation, you can think of a micro bet as being how long is this slide going to take, or the next slide, or the next, keeping you gripped and engaged throughout the entire presentation. I hope you are anyway, but if not, should help. So we have a lot of new betting content types, but how many more? Each year, we are consistently offering more and more markets. The diagram behind me visualizes how many unique markets we've taken bets on for the MLB, NBA, and NFL over the last few years. And we can see that this has almost doubled in some cases. And we also haven't come close to exhausting the number of markets that we can offer with the information that we have. And this isn't the whole story. To ensure that we've had a best-in-class offering, whilst ensuring we can work on strategic initiatives to position ourselves to be clear market leaders in the future, historically, some of these markets have come from third parties. And over the last 2 years, we've gone through great lengths to in-house the majority of these markets. And other than not needing to pay revenue share to these companies, we also have the clear benefit that by bringing these markets in-house and developing them in-house, we can seamlessly integrate them into our other betting products, namely same-game parlays.
And yeah, in the last few years, same-game parlays have become a huge part of the US sports gambling ecosystem. I think in most part because they're really fun. They exemplify one of the things that people like the most about gambling: the ability to risk a little bit to win a lot. And traditionally, when we thought about parlays, what we thought about is combining a combination of different bets into a single bet, all from different games. So you could parlay the Yankees and the Giants both to win tonight. And for us, that was very easy to calculate the odds of, because those are independent events. We could just multiply the probabilities of them together to generate the new odds. Same-game parlays, however, are exactly what they say on the tin. They're a combination of different bets that all take place in the same game. Unfortunately, that means they're no longer independent, and we actually have to calculate the correlation between those bets. An example of this might be, so Aaron offered you a bet at the start of our talk as to whether we go over or under 34 minutes. If you wanted to bet on us going under 34 minutes and me falling off the stage, that would be a very different thing. If I fell off the stage, you will spend 30 to 60 seconds laughing at me, and that would negatively impact the chance of our talk going under 34 minutes. And as I established earlier, as things become less likely, the odds that customers have to bet at becomes higher, so the eventual payout to you would be greater. However, this has massively changed how we've had to calculate things. While previously we could use single statistical estimators to predict individual markets or a set of related markets, that's no longer good enough. As Aaron already established, we now need to produce double the markets as we did previously. And now we also need to think about the correlations between markets, which would require a whole other set of models that would sit above those models. And that makes the old school solution untenable. So as SGPs and live betting started to gain popularity several years ago, we moved to an approach called Monte Carlo simulation. And Monte Carlo simulation was invented during World War II as part of the Manhattan Project. It's a way of modeling random probabilistic events by simulating them tens or hundreds of thousands of times and then counting the final state. A more tactile example than nuclear physics might be something people will have studied in high school stats class. If you wanted to measure the fairness of a six-sided die, an effective, albeit slightly time-consuming way of measuring that would be to roll that dice thousands and thousands of times and count how many times each number comes up. If each number comes up roughly the same amount of the time, you can be certain that die is fair. And our simulation engine in baseball works exactly the same way. We start at the first pitch of the game, and we simulate what happens in the first plate appearance. Is it a single, a strikeout, a home run, or a multitude of other outcomes? Next, we're updating the game state, which is effectively an embedding of what's already happened in the game in our simulation's eyes. Have there been any home runs scored or outs? Which inning are we in? After that, we're predicting whether any runners attempt a stolen base, and if they do attempt a stolen base, whether they're successful. And lastly, we simulate whether there are any player changes. Has the starting pitcher got off to a bad start and been pulled, or have any pinch hitters come in? At each decision point in our simulation, we have specifically trained machine learning models to predict the outcome that we're looking to predict. And the beauty is, once we're done simulating, we can just count what happens. If you want to bet on Jun-Hyu Lee hitting a home run and the Giants winning tomorrow, we can just count the number of simulations where both of those events occur and divide by the total number of simulations we've ran. And that's our probability. Now, Monte Carlo simulations are great, and they solve a lot of our problems, but they also present some new challenges.
So we established already our simulations need to price over 300 markets concurrently. And for us, even the slightest inaccuracy could lead to losses of hundreds of thousands of dollars in a matter of minutes. We could make our predictions more accurate by running more simulations, or by making our underlying machine learning models or simulation itself more complex. But this would come at the cost of latency. During a calculation, we'll freeze our prices. This is to ensure that we're never offering prices on outdated information. But this means that a customer won't be able to place their bet, leading to a worse experience and just more friction in general. So in live matches, we aim to meet a sub-second SLA for each of our components. This means that at any point in time, we always have a trade-off. Do we want to be more accurate, or do we want to be faster? On top of that, we need to account for a whole host of other issues. For example, the data in our feed is incorrect. I'm sure everyone in this room runs into data quality issues constantly. And on top of that, the information in the feed may not capture everything going on in the match that you yourself will be able to see with your eyes. And of course, models can only predict on the information they've been trained on. Anything you want to say about the torpedo bat situation?
The less we say about the torpedo bat, the better.
Okay, moving swiftly on. So we've established what we do, but how do we actually do it? This slide is primarily stolen from our colleague, Rohan Shankar, who talked at the summit last year. So if you want to see more detail on this, there's a recording on, I think, YouTube, where you can just go back and take a look at it. So we'll touch on some of the key details. The black box model that we want to understand here is in the bottom right-hand side of the picture on the left, our simulation engine. At its core, this is a Flask application deployed in Kubernetes that receives a HTTP request containing the current game state and some other information. It then will perform the simulation and publish information downstream, which results in the prices that the customers will see. The simulation engine, as we mentioned before, contains many different machine learning models. These are all trained on Databricks and injected into our deployed application. The other key part in this diagram is the feature store publisher on the left-hand side. This allows us to generate some slightly slower moving, but not quite static information within Databricks, publish it to Kafka, and then this will get aggregated together with information like our real-time feeds and game state, joined together to create our final payload, which the simulation engine will predict from. And specifically for today, a key input, which is derived in Databricks and published through the feature store publisher, is our player ratings.
Yeah, so similarly to last slide, this slide's actually referential to a talk that we did last year. And our colleagues in Barney and Phi gave a whole talk on our player ratings. So I'll keep this super brief. The important things to know about our player ratings are they're what I call Kalman filters, which means at any given moment, they're predicting two things, and they're updating continuously. The first is how good a player is at a given thing. So behind me, what you're seeing is a Kalman filter fit to predict the speed at which Usain Bolt will run 100 meters at any given point in his career. The second thing they keep track of is how confident we are in that estimate, or their uncertainty of prediction. Effectively, you can think of Kalman filters as coming with their own confidence intervals. Importantly for us in baseball is that our model's fundamentally player-driven. At any given moment in our sim, we're aware of which pitchers at the plate, which batters in the game, and who's on base. And so we need our player ratings to drive the accuracy of our predictions. We train all of our ratings on Databricks, and if you'd like to know more, I really recommend you checking out our talk from last year, which will be linked in our slides. Okay, that was a long introduction. And to give a peek behind the curtain, the timer I set sort of faked. We have a timer right here, so I can say that we've been at about 15 minutes so far. How are people feeling about their bet? Does anyone want to cash out? Jokes aside, there's three key things that I want to make sure that we've conveyed before we move into the meat of our presentation. The first is that we're modeling baseball using a simulation-based approach that's fundamentally player-driven. The second is that that's a really hard problem to solve. And the third is that making that problem harder is the fact that our models are heavily constrained by latency-based SLAs. So with that in mind, how do we really do it? We get help. And by that, what I mean is we hand some of the reins of our models to our traders, who are based in Vegas and are sport experts with decades of experience, who help fill in some of the gaps where our models would perform better with some human interaction. In these situations, traders are driving the model using our player ratings, which are the exact same ratings I talked about before. But here's an example of the inputs that the traders might actually have at their disposal. There we go. Phew. So the goal of our ratings is to make them as intuitive as possible, so that traders are able to interact with them by changing our opinions on player abilities. So, for example, the second column in this screenshot is the batter's singles rating against right-handed pitchers. And what that is a rating that's been fit on their historical rate of hitting singles. So in an example where a batter was off to a hot start, as is a couple of instances within that screenshot, a trader might choose to increase their singles rating in order to simulate more singles, which would then flow through our simulation and affect all of our other pricing. But in total, we have over 50 player ratings that traders can interact with, which leads us to the fundamental problem that Aaron has helped us to solve. How can traders see the effects of their actions in real time?
Well, our models are complex, meaning that they are even harder to explain. So we come to the crux of our business problem. How can we let our traders know in real time how to tailor their inputs to interact with our black box model, simulation model, so they can get the output that they want, namely accurate, customer-focused pricing? So let's take a quick look at what we've built. On screen, you'll see a very simplified example of what we've built, and we've done this just to highlight some of the key information. The demo is during a live real match between the Rays and the Blue Jays, and calculations will be occurring in the background in real time. In this demo dash, we make it so the user has to select the latest calculation ID, and this is mainly just to show you guys that stuff is actually happening, because we don't want our prices jumping around massively in real games. So on the left, we can see the front end of our sportsbook, and this is what our customers would see. You can see the exact final prices, and it'd be where you would place your bets. On the right-hand side is the information that is being streamed directly from our sports engine. For this specific game, we visualized a number of the key insights from the model internals. For example, the mean number of doubles any player or either of the teams is predicted to make within the match. And a key thing to note for this is that this is an exact view of what our model is thinking at that point in time, prior to any of the other system changes that we may apply to it. A few things like that may be margination to our prices or things like price shading. So to power this, as we all know, we're going to talk about real-time streaming. So this slide is taken from a Databricks tutorial because they do it so well. But Databricks structured streaming is a scalable, fault-tolerant, and exactly one stream processing engine built on Apache Spark. It lets you write your streaming jobs using the exact same API that you would your batch job. And that means that it's really easy to write the code, and it's really easy to transfer the existing code you've already written. You can stream from a variety of data sources like Kafka or Delta tables, and then you can also write to a variety of other sources. There's also a variety of different ways that you can write to this unbounded table, whether that be appending, overwriting, or updating the information there based on your use case. And then on this unbounded table, you're able to query and perform aggregations in real time. whether that's to power your analytics or to use the information as inputs for your machine learning models. So what is the data that we're streaming? Counters. This is the primary output of our simulation engine that we're concerned with today. And you can basically just think of them as box scores. As Ethan said, we're able to count what's happened during our simulations. And it means that we can see the number of hits, RBIs, doubles, home runs that each individual player or teams have had throughout the match. And the beauty of this is we can simply extend our simulation to count more things whenever we want, and we can go as granular as we want to. And now, this is incredibly easy to look at and understand what is going on. But as we've discussed, we have a lot more of these. Depending on the sport, we have up to 100,000 simulations. And what we displayed on the previous slide of the box score is far less information than we're actually producing for that sport. And clearly, when I look at this, I've got no idea what's going on anymore. So, as I'm sure everyone in this room would do, when you're met with a vast amount of data that you don't really understand when you look at it, you graph it. So here, we're just simply charting the distribution of home runs within a game, and instantly it's far clearer. Previously, our traders would have seen the most balanced line, which in this case would have been 0.5 home runs, and they would have seen that there was about an 80% chance of hitting the under. For us, as a sportsbook, it's really important that now we can see this entire distribution, we can see the slivers at 3 and 4 home runs, because as we talked about, the longer the odds, the more money we have to offer a customer if they win. So getting these correct and visualizing that for our traders is incredibly important. So let's move on to a lucid of our implementation. Our simulation engine writes the counters to a Kafka topic, which can be seen in the bottom left of this diagram. Within Databricks, we then have 2 streaming tasks. The first one just writes the raw information from our Kafka topic to a delta table within Databricks. And this can be reused for just any Kafka topic. The second task then reads from this first stream table, actually performs our transformations that we're interested in, and then writes it to a second delta table. From here, we then query and visualize this information within Sigma. And this is really easy to do. You just set up a SQL warehouse, open a connection, and then bang, it's there. You can see it in real time. You could easily visualize this information within Databricks dashboards. It works completely fine. It's just at DraftKings, Sigma is one of our main observability tools, and as a business scales, it's easier just to have a single pane to view all of your dashboards in. So this gives us a clear, scalable framework that we can extend to any sport, any Kafka topic, and really any information we want incredibly easily. So in the context of the tutorial that we showed earlier, with the data stream and your unbounded table, for us, our data stream is our counters information. And for this, we're going to assume that we have a dedicated Kafka topic per sport. Each message within this topic will be for a specific match, for a specific initial generating request, and for a specific batch of resultant counters. So when I talk about a batch of resultant counters, what I mean is that for request ID 1111, we can see that we have 3 counter batches. And we can imagine that our simulation engine, in this case, is producing 60,000 simulations. We will then batch these into sets of 20,000 simulations each. If we didn't do this, then our messages would just get far, far too big, and they only get bigger as we add more information that we want to track. Our architects warned us that this could cause degradation across our entire Kafka broker, so we thought, well, maybe we should stop abusing Kafka and start treating it how it should be, and split these into smaller messages. And here, this is where the streaming just comes in clutch. It lets us process large quantities of data quickly and handles aggregations of these statistics across each of these batches easily. And at this point, we've spoken about they're quite large, but what's our throughput of these messages? The numbers on the screen are the mean number of calculations across the top 10 days of each of the listed sports. So for basketball, we can see we were processing 167,000 requests per day, meaning we had 167,000 sets of counters before we started batching them. And it's also important to note these aren't just nicely spread out across the day. They come in absolute flurries as all of these matches start, and they start when people are awake and can watch them. So most of them are at the same time. So now let's take a very quick look at the code. All of the slides will be made available as PDFs after, so just going to breeze through them, and you can take a look later if you need to. So first off, for streaming, you need to configure a Spark session, and we optimize it for our use case for streaming. We configure it to use RocksDB for state management due to its efficiency, and then also set a couple of bits of checkpointing. And then after this, we set up our pipeline to read our raw data from Kafka and write it to a Delta table. First, the build filtered data frame function creates a streaming PySpark data frame sourced from the specified Kafka topic. And as messages arrive, they're read into this data frame, and we include our Kafka headers because they have a lot of important information for us. We then, specifically to our use case, filter out a load of messages that are labeled as heartbeat signals, and we use these to monitor our service health during low traffic periods, like the NFL off-season. So when the season comes around, we know that it's still alive and working. Firstly, we define our streaming query that writes the filtered data frame to the raw stream table in append mode, with each message becoming a new row in that table. After this, we then have our actual counter transform set of code, and this is basically identical to the last set of code, but instead of streaming from the Kafka topic, we just stream from the previous Delta table, perform our transformations, and then write it as a new Delta table. There's quite a lot of code that we've hidden away in the transform step, but at a high level, this is all the code that you actually need to get streaming set up and running. It's really easy. But there's an awful lot more that you can do with this, and that we do at DraftKings that we're not going to cover in this talk. The two key ones I want to talk about here are stream joining and windowed aggregations. So within DraftKings, surrounding our components, we're primarily a microservice-driven architecture which communicates via Kafka. Due to our heavy investments over the years in telemetry, we're able to trace our pricing updates throughout all of the components with ease by attaching as headers certain IDs to track different things, basically. This means we're able to join any information from any of our Kafka topics in real time to give a view into what the entire system is thinking about that one pricing update. And we're even able to join this into other information like bet flow, liability, or like we talked about earlier, the player ratings that were actually driving the requests that we've seen go through. And the second one that I want to touch on quickly is the windowed aggregations. We can provide information like what were the last 3 pitch types that the pitcher threw to our traders if we think that will help them make more informed decisions on how the rest of the inning is going to play out.
Okay, so now we know how it works. I think it's worth going into a little bit more depth about why it's important and how the interface between the traders and the models really work. And underpinning all of this has been sort of an important shift we've gone under over the last 6 to 9 months, where previously we thought of our models as these super powerful machines that just spit out the empirical truth about what was going to happen in a baseball game. Now we sort of see them more as a sandbox. Like, their function is to take a set of pre-match player beliefs, pass them through a simulation, and saying, given we believe these things about the players, what's going to happen? And if the market or our traders disagree with our historically fit ratings, then they can trade those. And those changes will flow through every market that we create and any SGP a customer could possibly create. So why are we doing this? And I touched on this a little bit earlier, but the first and most obvious reason is to fill in the gaps where the model is underperforming. And that might be because we're missing data, the corners we've had to cut to hit our latency SLAs, or recent form that we've been slow to pick up on. And the next 2 reasons are more philosophical, but they're worth touching on briefly for the purposes of this presentation. And they're to do with a sportsbook's risk tolerance towards liability. So when I say liability, what I mean is the amount that you have to pay the customer in the event of a bet paying out. And we're expecting around $150 billion bet on sport in the US next year. So when you're one of the major sportsbooks in that market, it's really easy to rack up liability. So in cases where we have too much liability on a specific selection, traders might choose to change our pricing to encourage betting on the other side of that market, which is a process called balancing the book. Similarly, if you're ever off market, and by that what I mean is you're hanging a price that promises a much better return to the customer than the rest of the market, it's very easy to rack up a lot of liability. So in situations like that, traders might choose, even if we're confident in our pricing, to move our price back in line with the market in order not to rack up too much liability. So let's look at a real-world example. And this is the same simplified dashboard that Aaron was talking to earlier. But what we're looking at in this video is what might need to happen if there's late news of a pitcher change. And in this case, it's a switch from a left-handed pitcher to a right-hander. Right now, you can see on the dashboard that each team's expected plate appearances versus left-handed pitchers, and one team has a very different number. And below that, you can see how that is distributed across the batting order. Off screen at the start of the video, the traders changed the expected starting pitcher, and now we're about to see the calculation come through in the dashboard. He's going to be publishing the statistic for the new pitcher right now, and once he does so, the dashboard should update, and we'll see the expected plate appearances for each team become much more similar. And that should happen now. And previously, a change like this would cause absolute carnage for us. All of our player ratings are split by historical performance against left-handed and right-handed pitchers. So in a change like this, we'd expect our prices to jump a fair amount. And for the most part, we're more confident in those new prices once the pitcher has been changed. However, traders would still have to freeze all of our pricing and manually go through each player market in order to make sure that we were confident publishing those prices. But now that process is a lot quicker, because now, with the dashboard that Aaron's built, traders can see the impact on every player within one simple visualization, like you can see here for the hits projections for that game. And because we've been able to extend the counter-streaming dashboard to every statistic that we keep track of in our sim, traders can see every piece of key information that they need to know in real time, quickly. So what's been the impact for the business? Well, the obvious one is that it's now a lot quicker for us to price up games. Between some changes on the modeling side and this dashboard, it's now around 30% quicker to get our prices on site. And that was our final roadblock for releasing fully originated player props, which in turn opens up avenues for further expansion to our player props offering and reduces our reliance on third-party feeds. And thanks to examples like the one I just went through, we also have increased uptime of our markets, with fewer instances of bad pricing making it onto site.
So that's our presentation. At the start, we said we'd tell you how to explain the unexplainable in real time so that you can drive your models better and get more buy-in from your stakeholders. And at DraftKings, the solution we've talked about has been important to us because...
Well, it's important because in order to improve our pricing, there are more and more instances where we'd expect humans to be able to interact with the model in real time. And in order to be able to make those decisions, they need real-time data.
Yeah, and we've done this using a simple, scalable, fault-tolerant framework, which is incredibly easy to implement and also wildly customizable. So thank you for spending the time listening to me and Ethan. I want to mention that our colleagues, Greg and Monica, are going to be doing a talk tomorrow on lessons learned on their real-time implementation for fraud detection. So I'd highly recommend attending that. I think it'll be at like 11 tomorrow. Yeah, Ethan, what's our time count?
We made it to 34 minutes on the dot. This is a great line.
It's so good.
Thank you, everyone.